All right, structural design. What is structural design? How is that different from like architecture design or interior design or like design? Any thoughts? What is structural design? Calculating the sections of the beams and the columns. Calculate what about them?
Dimensions.
Yes. Load. Did load, live load, perfect. That's very specific. I like that. We'll talk about this today. Ultimate state, limit state. Okay, do you specify the material?
Yes.
Yes. Do you specify the geometry? When you produce a drawing, do you give kind of dimensions and where to put everything? Perfect. Yes.
It's only for steel buildings or?
Structural design is only for steel buildings?
Just asking.
Is that your question? Like, what do you mean? Okay, Rana, you had a comment?
Isn't structural design, yes, there's steel structures, but then also concrete structures?
Yes.
There's the steel design itself, the internal steel of the column, the beams, the slabs.
Structural design is for any structure. As a matter of fact, if you're building a space rocket, I know like SpaceX, they would hire a structural engineer to design the structure. And then you go there and you figure out what you want to build the rocket from. Do you want to build it from steel, from composite material, from fibers, from whatever? So that's why you study materials. That's a different module. You study structural analysis. That's a different module. And then you bring everything here to design so that you can design buildings, structures, or whatever you want. So can you think of examples of structures? What are structures that engineers can design? Bridges. Beautiful. Tunnels. Okay, yes, that's a very good example. You can design a tunnel. And towers. So I have an example here of a tower. And you can actually see some like exterior structural elements. Like these diagonals, these trusses. We know trusses from structural analysis. These are structural elements. The structural engineer count on these big, huge trusses on the outside of the tower to take the wind loads. You guys said towers, tunnels, bridges, anything else? Yes, dams. So that would be a structure holding water. What's that? Yeah, like an open channel, like an open water channel. Big pipes. You can design big pipes. Normal buildings, yeah, just like a building like this, a hospital, a hotel, university building, absolutely. A house, a residential building, a mall. What's that? Yes, pretty much everything, yes. And that's the power of structural design. So these are the scopes that you can have for your career. You can specialize. I personally love tall buildings. I've spent a lot of time analyzing them, understanding how they work under different loads, what are the loads on them, wind loads, seismic loads, things like that. You can specialize in like ports and water structures. So what if like you have a big ship that might actually exert load on the port or the dock? What if you're designing a dock in a very cold environment that will have ice chunks ramming into your structure? So regardless of what structure you decide to design, you will have to look at the specific problem, but the foundations are mostly the same, and that's what we're going to do in this module. We're going to explore the foundations in order to enable you the best chance to succeed in whatever you pick to design. Things could get super complicated. Like, imagine someone hires you to design the truss for this roof. My first thought would be like, what is this? Like, why are you trying to create that much complexity? And this is where the architect come in mind. They might kind of work with the client, like we want something to look a special way, and we want spaces that look like that. And once they figure out how they want it to look, they bring the designer or the engineer. And they kind of hit them with this kind of image, and it will be your job to break down the complexity of the structure into beams and columns and moments and shear forces, pick the material, figure out the stresses, and issue construction drawings so that the workers on site can build something as complicated as that. You can get curved and round and circular steel frames. You can get like space trusses, like truss joints that take curves and arches. So things can get pretty complex, but at the bottom of it is just the simple concepts. Like this might look intimidating, but at the very core of it is just like how to design the simple beam, the simple column, the forces on it, and so on and so forth. And this is pretty much where we're gonna start. To use the bridge example, you can absolutely build bridges, industrial buildings, even like offshore structures. So these structures are very interesting. They sit either on the bottom of the ocean, or like if the ocean is too deep, some of them will have like very interesting floating mechanisms to keep it in place. All right, so I hope this gives you an idea of what you can do with this module. It's pretty interesting, and just the knowledge of it will add a lot of value. What are we going to study in Structural Design 1? Yes? Does that make sense? Okay, we are going to study 3 main construction materials, designing with 3 main ones. We'll focus on steel, design of steel. And then we'll take an introduction to timber or wood design. And then we'll start the design of concrete. We'll continue it next term. And then we'll dedicate big chunk of structural design 2 for concrete. Obviously, concrete is one of the most used construction material, especially in our community. So it's very important to get a very strong handle, especially if you would like to work as a designer. If you work in a consulting company, spend all your day in the office thinking, referencing the codes, crunching numbers. This would be something that you would do on a daily basis. If you like to be in construction or project management, when you sit in a meeting and you understand how the design is done, you will bring so much value to your team. You understand what the opposite person from the table is talking about, and it will give you like a level of comfort, and you can be a professional and benefit your team much better just by understanding these concepts. So regardless of what you want to do, it's very important to explore these concepts. Let me share with you what we're going to do in steel. Steel sections look something like this. You can have a steel section that has a cross section like an I, like a C, circle, tube, and then you use them using connections. The connections could have bolts, or you can weld them. You can weld steel to steel and create a structure. Columns and beams, and then floors, and then build the entire structure. We first want to understand the basics or introduction. That's what we're going to do today. Starting next week or next lecture, we'll talk about bending design. Designing a beam, let's say a simple beam like this, to be strong enough to resist the bending moment on it. Structural analysis 1 already introduced us how to calculate the maximum value for bending. In structural design, we're going to right away calculate the bending and use it to design the section. See how big of a section we need to consider. That we'll deal with this next class. The lecture afterwards, we'll talk about shear design. So now the shear force diagram, the section you choose needs to be strong enough to resist shear. I will also talk about checking deflection, which is something you guys did in the project. That was a task, so you should have a pretty good idea. We'll go in detail how it works. And then from there, we'll explore timber and concrete. So, I talked about the codes and standards. It's very, very important to get these standards on the left side. You can think of this as the law. You should never contradict or break a very specific statement in these codes. Your design will be considered not up to standard if you conflict or you contradict a main principle in these codes. Having said that, these codes are made by like fellow engineers. They're not like, they're open for improvement. And that's why you will find like a date on it. Like this one is like 2012, this was in a different version because there are different versions and updates. The knowledge of engineering is constantly improving, and it only makes sense to improve the law and improve the text that all engineers reference to. Having said that, we're individuals and human beings, and if we're both designing a project, I might have like an idea and be so proud of it and think it's brilliant, and you might think, oh, this will never work, I have a better idea. So we should be able to work within what these codes allow. Both of us, we should never contradict what's in this, what's in these codes, and that's why it's very important to understand them and bring them. So I showed you the list. I need you to use your accounts and figure out a way to get it for the both sets. The bottom one is for the Egyptian code. The top one is for the European code. And because these documents are so important, there is a whole bunch of textbooks out there that explain in details how to use them. So you can find additional resources that can guide you through these textbooks. Here is the specific list. On the left side is the European codes. I already told you what are the ones that we will need. We will need the steel structure 1, it's Eurocode 3. Steel design is Eurocode 3. Eurocode 5 is timber. Eurocode 2 is concrete. For the Egyptian code, 201 is for loads. We'll also need 203 for concrete, 205 for steel. Let's move on to the structural design process. I already touched a little bit on this. So you were hired to design a residential building, like a tower, 20-story building. Where do you start? First step is calculate the load and the structural system. Do you remember what was the first requirement in your maybe like presentation or like the final coursework for the project? What was the first thing I asked you to do about the structure? Was that? Yes, that was definitely there. I was hoping someone remember the structural layout. Was that something you did at the beginning or at the very end of the project? At the very beginning, the structural layout. I need to figure out where the columns are, where the beams are, and the walls in order to get the structural system and calculate the loads on it. I'll show you how this works. From there, you do structure analysis. Use structure analysis 1 and 2, and get the material properties. Your client might ask you to do some alternatives. How much it will cost if I build my building in concrete? How much it will cost if I build it in steel? So you might kind of crunch some numbers and say, if you design it by steel, those are the dimensions, and you reference the steel code. If you design it by concrete, those are the dimensions, and you can do like estimation. That was another task in the group project, I think, to estimate the quantity. And from there, your client can do an informed decision. Once you pick which material you will use, let's say you will design your structure out of steel, then you do design, structure design, what we do now, and detailing, issue drawings. Like when beam on grid line A intersects with a column on grid line 1, the connection would look like this, C section 1-1, something like that. So this is what I mean by detailing. So very quickly, let's talk about structural systems. Let's say you're trying to build a bridge. This is the finished product. So how do you break it down into a structural system? A structural system means where are the structural elements? Do you guys know what are the structural elements?
Yes.
What are they?
Columns and beams.
Columns, beams, slabs. Thank you. So where are the beams for this bridge? It's these two tubes. Can you see these kind of rectangular tubes?
Yeah.
That would be the beam. So your structure analysis would look something like this, like a beam on supports. And we know pretty much how to get that. Reactions, distributed load, things like that. Let's say you're trying to build an industrial building, a factory or something like that. So you might be able to come up with a structural system that has these frames every so often, and then beams on top of it and cross bracing. That's what I mean by the structural system. That's step number one. You need to put the structural system and calculate the loads on it. And we'll talk about the loads in a second. This is the 4 main construction materials that you can use to build structures. Concrete, I would say, is the most common one in our community. Steel, obviously, what we're going to focus on in this module. Concrete is an interesting term. I would reference concrete as reinforced concrete. That's a material. Reinforced concrete has 2 materials, has concrete and steel. Reinforced concrete. If you say concrete, that might indicate or suggest you're talking about plain concrete, just like fresh concrete with no reinforcement. These 2 materials, concrete with no reinforcement and reinforced concrete, behave differently. So they're different things. So let's say reinforced concrete, steel, these are the steel sections. You connect the joints either bolted or welded. There are 2 more materials that you can build with. Wood or timber. It's cheaper and more common in communities where wood is more affordable. So typically in North America, in the United States, in Canada, in Europe as well, there is big forests, logging, and a source of obtaining wood is available. So it makes more sense to build small buildings, like small homes, from wood structures. And not a lot of engineers in our community understand the principles of working with wood. So if you get the basics, you already are setting yourself ahead of the competition. You have an idea about how wood structures work, which is something I think is an asset. The 4th type of material you can use with is masonry, like bricks, like Lego, like building with Lego, and you put mortar. It's very common to use it as a partition wall, like those red blocks that you see that we use in buildings. Typically, we don't use them as a structural element. We just use them to separate this big room into 2 rooms. But you can actually use them to build an actual building without concrete, but you cannot go as high as concrete structures. If you're building a skyscraper, you obviously need reinforced concrete and maybe steel. Those are like for more smaller buildings. Any questions so far? Things are going okay? All right, so I want to talk, before we switch gears and we get some examples of what the actual specific design I want you to do, I want to have a general idea about how do you design a section of steel. Well, we might as well understand how a steel section might fail. There are different ways that a steel section could fail. So when you're designing it, you're making sure that it's not going to fail like this. It's not going to fail in like compression like this. And it's not going to buckle like this. And then you fulfill the checklist. Okay, this beam is good for this type of failure, strong enough. It's strong enough for this type of failure. It's strong enough for this type of failure. And then this beam should be sufficient to carry the load. And then you put your name on it, take responsibility of the weight of the structure and the people on it, and that is basically the structural design. So what we're going to do every time we talk about a design of a member, whether that a beam, a column, a steel deck, a cross bracing, we will go through the steps. First, check that the beam is strong enough to resist lateral torsion buckling. This type of failure where the upper flange kind of goes sideways and the bottom flange stays in the same place. So we'll learn how to check that. And the codes, the steel code, will give you the equation. If you want the beam to be strong enough, you follow this formula, things like that. If you're designing a column, you need to make sure that it's not gonna buckle. It's not gonna go like sideways like that, or the flanges are not gonna work. And that's the essence of structural design. All right, now a big, very important question. What are the states or the loads that you use to design the structure? This is a concept that evolved with time. Structural engineers, when they first experimented with designing buildings, you can think of like ancient times, like the Roman time, or even like the Pharaoh's time. Next time you go see a temple, or you see like a tomb from ancient Egypt, you might kind of take a look at the size of like the columns and the size of like the doors. You would see like, because the entire structure is just like solid stone with like dead weight, it has like huge dimensions, huge diameter for like the temple, big blocks. That's because the assumption was, all right, I will see how much this piece of stone can take. I will put like 2 blocks on top of it. If it's still, if it didn't fail, I'll add more onto it till like it fails, and then I will note, okay, this type of stone can take 2 blocks or 3 blocks. As things got more interesting and more sophisticated, we realized that there are 2 states of the building that you need to design for. There are 2 cases that you need to make sure that the building is functioning properly. The first state is called the ultimate limit state. If you load this structure all the way to the point it's about to fail, is it going to be able to withstand the loads, or the material is going to give away and is going to fail? So that's called the ultimate limit state. And I will talk about the load factors we use to design the structure for this ultimate state failure. It's like if you load it to the max, is it going to take the maximum load or is it going to fail? There is another state that is way less than the ultimate load, way less than the maximum capacity. I want to know, under our normal weight, under the normal use, the everyday use of this classroom, is the floor gonna vibrate too much when we walk on it, or is it gonna be comfortable? It has nothing to do with safety, it has to do with comfort of the users and the serviceability of the building. Hence the name, the service limit state. And I'll talk about the load factors that are associated with that. So whenever the term ultimate limit state or service limit state come up, I want you to think of 2 different things. Ultimate limit state, this is the state of the building to avoid these pictures, to avoid like a structural failure. This used to be a column. It was loaded so much to the point like the internal rebars exploded out of the side. That's the ultimate limit state. So if the building is not designed properly for ultimate limit state, you can result into failure. It's very dangerous to break this state of design. The service limit state mainly has to do with deformations. If it's windy outside, if there's very high speed winds, is the structure going to move sideways like in a noticeable way? Like, are we going to feel uncomfortable with like the shaking of the building because of wind? Or if the next room there is a gym and they're having like a very hyperactive class, are we going to feel their vibration here? It has to do with the serviceability of the structure. So these are the 2 limit states that we will design for, and they have different load combinations. So each code, each standard will tell you the load combinations you should use for each case of loading. So let's consider the ultimate limit state. This here is the exact text from the European code, from the Eurocode. It defines what the ultimate limit state is, and it breaks it down by the types of loading. There are four, let's say five, main types of loading. The dead load, that includes the self-weight of the structure and anything that is permanently in the structure. The live load, which is the weight of the users, us, our furniture, our luggage, anything that comes in and out of the structure. If that structure was a parking structure, the cars would be the live load. Cars in the morning, people are going to work, they park in the parkade. At the end of the day, cars leave. So that's the second type. The third type is wind loads. We will learn probably in the next term project how to calculate wind loads on structures. The fourth, very important load, earthquake. Some regions in the world are very high active seismic region. There are usually violent ground movements that can affect the loads on the structure. The fifth one is not very common in our community, but again, if you live or designing a building in a very cold environment, you will have to account for snow load. In the winter, you get blizzards and snow will pile up on the roof of the structure. So those are the five loads. I need you to understand what the Eurocode and the Egyptian code call these five loads. The Egyptian code will call the dead load, D. The European code will call the dead load GK. So now it's a term of like picking a book and starting working. You understand what you need to do. You need to get dead load, live load, and the combinations. Now, where is your project being built? Built in North America. Fine. Where? Canada, United States. All right, let's get the Canadian code and look up what did he call the dead load, what did he call the live load, and use their load combination. All right. The ultimate limit state would avoid the complete collapse of the structure. The service limit state has to do with unfactored loads. So let me just go for a second and notice that you designed the structure not just like for one, the dead load, the actual amount of dead load, and actual amount of live load. You exaggerate, you increase a load factor, and in the next slide, I will tell you exactly why you increase the load than the actual value. So for ultimate limit state, it's very important. To avoid the collapse of the structure, you increase the load. And you actually decrease the strength of the material by a factor. That depends on very specific rules, and it's all referenced in the code. You need to follow the code. So just notice this in reference to the next slide. This is ultimate limit state. For the European code, you use 1.3, the dead load, plus 1.5, the live load, to design the structure to avoid collapse. If you are designing for vibration, if you want to check the vibration, that the people at the top are not feeling the vibration of the machinery and the computers in the bottom, or when the people on the top start using their cubicles, the slab or the floor is not deflecting too much that it's noticeable to the people underneath it, or they start breaking the ceiling tiles or the light fixtures because the floor is deforming too much, it's causing damage. So if it's serviceability, deflection, deformation, or vibration, use the actual dead and actual live. Just use the actual conditions the structure will be exposed to. Does that make any sense? Do you understand the difference between service load and ultimate load? Ultimate is factored. Service is the actual thing. So the question comes, why? Why do we increase the load to avoid failure?
Road design.
What's that?
Road design.
Road design, what about it?
Yeah,
You increase the load? Okay.
Third purpose.
I like that. Safety factor. What do you mean by safety factor?
وصل الليميت يعني له المساحة يعني.
Because the consequences are catastrophic. Like this is a small example. This is a garage, and this is example of the wind load, the snow load, the fifth type of load that I talked to you about. In the winter, snow will pile up significantly on these roof trusses. Can you see the roof trusses? So if there is too much snow, it will crush the roof. Okay, so how much is too much snow? Do you know exactly how on this winter the amount of snow that will fall on this house? There is like a probability. It is a probability. You could have like a terrible winter and the snow is huge, and you could might not get snow at all. So this introduced that the load is a probability function. We're not 100% absolutely certain the exact weight of snow that will fall on the building. Same thing with wind. We're not sure exactly what will be the wind speed every day, but we can guess. We can guess in 50 years from now, the worst storm will have a wind speed about that much kilometer per hour. So I want you to understand this, the significance of this curve. This curve is a probability function. Most probably, the load will be at this value. But there is a very small chance that the load might be higher than that. And there's also a chance that the load could be lower. Believe it or not, this applies to the strength of the material you're using to build with. So let me ask you this. Let's say you're designing a structure from concrete. What is the strength of concrete that you would use to build a structure? What would be the strength of concrete that you would use to build a structure? Like, what's that? It's a residential, let's say a residential building. You're designing a residential building using concrete. How strong you want your concrete to be? I love that. C35. What is the 35? It's the maximum compression that it can take. It's an actual number. It's 35 MPa. The actual compression it can take. What are the chances that you take a cube to the lab and you press the run button on the machine and it will give you exactly 35 MPa? Is there a chance that your cube will resist a little bit higher than 35? No? It will always be 35? Maybe. There is a probability. Do you know what I'm saying? Well, what is concrete made out of? Sand, water, cement, and we're humans, right? Like you shovel the sand and you put it in the mixer, or you use a more precise way in order to have like some quality control on your product. The better your quality control is, the more consistent your cubes will achieve the 35. Having said that, there is a chance that something might go wrong and the concrete cube achieves less than the design value. That's why we use safety factors, because I want to increase the load a little bit and reduce the material a little bit to create like a factor of safety to avoid a scenario like this. So the more you practice and the more you apply the principles, most probably you will need and come and revisit this. It took me a while to understand this concept. Like, why do we increase the load? And how do you figure out, is it 1.4 or 1.5? How do they come up with this? They come up with it from the probability that there is a percentage that the wind load or the snow load might exceed the design value. Same thing with the material. Steel usually is produced in factories with very precise measurements, so the factor of safety or the reduction in material is usually small. Concrete is mixed on site. You can have it mixed in trucks, so there could be more variations, so you need to take a different reduction factor for different materials. We'll revisit this every time we choose to design a new material. Questions so far? All right, let's say we want to design this structure. You break it down into elements. We'll learn the design of beams, columns, we can apply these concepts to different elements of the load. The first step is to calculate the load on the structural layout. So you come up with this plan. This is the first step that you guys did for the project last term. I asked you, get the location of the columns, put the location of the beams, and next step, I already asked you, get dead load and live load on the beams. So that's obviously the first step. You will have to connect very closely how the building is built with your analysis. So if building is built differently, you will have to consider that in how you calculate the load. This is a very simple way of loading. It's called a one-way system. A one-way system when you have the distance in the short side less than half the long side. If the distance in the short side less than half the long side, the load will go to the shorter direction. The load, if someone is standing here, their load will go to this beam and this beam. The slab is not going to get a chance to send their load to the far ends. That's what a one-way slab looks like. You can have like roof trusses like this, like secondary beams and main beams and steel deck on it. That's a typical example of a one-way slab. You pretty much did this calculation in the project. So I have this slide to show you. If you have a one-way system sitting on secondary beams, you just get half of the center line from left side, right side, get the load on it, and that would be called the tributary width or the tributary area that is supported by this beam. You figure out the load on it, the reactions, and then you go from there. Bending, moment diagram, and shear force diagram. There is another system of loading called two-way slabs. It's more common for concrete. We might not get a chance to use it this term, but definitely we will need it in the future. So I want you to know if the dimensions of the slab is bigger than one side, is less than half the other side, the load will go both ways. Some of the load will go in the x-axis, some of the load will go in the y-axis, and then the distribution will go like 45 degrees from the corners. So this is something, a reference for you to use. I got these numbers from the code. The code would tell you how much is a dead load for unreinforced concrete. How much is it for reinforced concrete? So you don't have to do a lot of guessing. Just reference the standard numbers. If you use something way less than that, and then there is a problem in your structure, an investigation will start. A third party will review your design, and they will point out that you assumed the weight of concrete less than the recommended value in the code. And that's a violation of the code. That's what I mean. Try never to contradict the main principles in these codes. They are binding. They are binding. They are part of the contract. You're having a contract with a developer to deliver them designs according to the European standards or to the Egyptian standards. So it's very important to follow these numbers. And it helps us too. We don't have to guess what's the weight of steel, what's the weight of the concrete. We can have it. This is from the Eurocode, and this is from the Egyptian code. We kind of assume our numbers, and you will find there's a lot of similarities because concrete is concrete. The variations can't be too big. This is the live load numbers. If you are designing an office building according to the Eurocode, you should design the floor for 2.5 kilonewton per meter squared live load. According to the Egyptian code, if you're doing an office building, you should design the floor for the same number, 2.5 kilonewton per meter squared. So there are similarities and there are differences. It's very important to reference the correct code. These are the load combinations. So the European code tells you for the dead loads, GK, you should use a ultimate limit state factor of 1.3 and service limit state factor of 1. The Egyptian code has two different values, one for like the concrete design and one for steel construction. The concrete design, it says 1.4 dead plus 1.46 plus 1.6 live. It's very important to use the correct factor load. If you start using different factor loads, you're designing a structure based on another standard. Now, this is what we're going to do in the tutorial. I want you to start understanding the design of a beam as like steps. First step, I will check the ultimate limit state check, which has to do with the ultimate limit state factors. That involves checking for bending capacity and shear capacity. And also, I want you to check the maximum deflection according to a different set of loading for the ultimate limit state factor. In order to get how strong this beam can resist bending, we will calculate the actual number next week. This week in the tutorial, we will get the next step, the first step, to get this number. The first step to get this number is to understand how strong the geometry of the section is. The section is divided into different classes. Class 1 section, Class 2, Class 3. Class 1 is very strong. It can take stresses. It can take stresses until the point of yield. Does this diagram ring a bell? You guys know what this diagram is? Yes, that's the relationship between stress on a steel element and the strain or deformation. The relationship is linear. The more load you put on steel, the more it deforms in a linear way, until it hits a very specific number called the yield stress. After the yield stress, the steel cannot take any more load. It will just keep on deforming without having more resistance. So a class 1 section can achieve yield in the entire section. It depends on the geometry. I will show you the formulas. If the section is not class 1, if it's not strong enough, the flanges will buckle. This is an example of like maybe class 3 or class 4. A weak, flimsy, small dimension section, when you load it, it will warp and buckle. It cannot get the maximum capacity of the material. If this section is like class 1, it's strong, it can develop yield without losing its shape, without like going like this. So how do we know? Is this beam going to be capable of taking the load without looking like this? Or is it going to, when it's overloaded, it's going to start warping? That's the first check that we will do in the tutorial. All right, how does that work? You reference the correct standard. The Egyptian standard has these figures, tables. The European standards has these figures. And what it says, look at the section you want to use. Let's say we want to use an I section or a box. You will look specifically at the dimensions of the section, the yield strength of the material, and follow these formulas that will tell you if this is a compact or class 1 section, or is it non-compact, or like class 2 or like flimsy section. That's the terminology for the Egyptian code. For the Eurocode, it says that's the class of the structure. That's the class of the section. If the beam dimensions fit these values, that would be class 1. If it fit the values below, that's class 2, and you have all the way till class 3. I need you to understand how to use the table. Best case scenario, if your section is class 1, it will fulfill these ranges. If it does not fulfill this range, you'll need to check the class below it and below it. how do you actually use these values? You just look at the definitions. If you're trying to design a beam for bending, you use the first column. It says part subjected to bending. If your beam has bending and axial load, you might be designing a column. You will need the two other columns. So if you're designing just for bending, you will use the first column. The definition of C is on the graph. This is the strain values on the section, and you get it from the figure below, from the bottom below. It will only make sense to kind of pick a section and try to do the analysis for, and I also want you to experiment with calculating the load on the structure. So that's pretty much all what I wanted to say. And any questions?